Our paper is titled Adaptive-Halting Policy Network for Early Classification. Consider the following problem. We are recording the vital signs of a patient who may or may not develop an infection. Each day, we observe more information quantifying their health status. Our task is to not only predict whether or not they will develop the infection, but also select the day at which we hand a clinician our prediction. Either yes, we believe they will get the infection, or no, we believe they will not get the infection. In this time-sensitive domain, the earlier we can provide a prediction, the more time a clinician has to react, therefore preventing negative outcomes. However, balancing earliness and accuracy introduces a multi-objective optimization problem with contradictory goals. On one hand, if we make a prediction early, we give the clinician enough time to react, but our prediction will likely be random because we have observed no signals. On the other hand, a late prediction will likely be accurate, but the clinician has no time to react. The optimal prediction time often lies somewhere in between. However, the quality of a prediction time depends heavily on the domain. For example, consider an outcome which requires an extremely invasive treatment. Such outcomes should be predicted with utmost care, emphasizing the need for accurate predictions. On the other hand, consider extremely harmful patient outcomes. In this case, even a hint of the outcome's development may be enough to warrant a prediction. To solve this problem, we propose a novel augmentation to a recurrent neural network, or RNN, leaning on the recent successes in deep learning to learn low-dimensional vector representations of time series. We pair an RNN, which is trained to generate a sequence of vector representations which discriminate between time series classes, with a probabilistic controller network, which learns a policy that interprets the RNN's vector representations and decides at each time step whether or not to halt the RNN if enough information has been modeled to warrant a classification. The controller samples actions from a parameterized distribution, treating its task as a Markov decision process, and is therefore trained using reinforcement learning techniques. We use one hyperparameter which constrains the controller's decisions, tuning the balance between earliness and accuracy. Once the controller decides to halt, a discriminator network interprets the current vector representation and predicts the class label. By building our model around state-of-the-art neural networks, our approach seamlessly scales with the ever-increasing rate at which high-dimensional and long time series are being collected. Using 7 datasets, we demonstrate our method outperforming state-of-the-art alternatives, effectively tuning between goals of earliness and accuracy with one hyperparameter. Thank you for watching. For more details, please look for our paper and feel free to reach out.